As we discussed before, the mass of the component parts of a nucleus do not necessarily bear much relation to the mass of the nucleus itself. It takes energy to hold together a nucleus, and this energy comes from the mass of its component parts. You might imagine that the bigger a nucleus, the more energy is required to keep it together, and you would be right. All those protons held together need to be kept from flying apart, and that takes more and more energy. However, the overall binding energy in a nucleus tells us far less than the binding energy per nucleon. In economic terms, it is the difference between the GDP of a country and the GDP per capita. The United States has a GDP of about $16 trillion, whereas China and India have a GDP of about 8 and 2 trillion respectively. However, the US is a rich country because its GDP is spread among 300 million people, and China and India are significantly poorer as they have populations of 1.4 and 1.2 billion respectively. The US has a GDP per capita of about $50,000, and China and India have GDP per capita of about 6,000 and 1,500. I'm not an economist, so please don't quote these figures. I only use them to demonstrate the differences between total figures and averaged figures. When you look at the total binding energy for a nucleus, you don't see much. But if you look at the binding energy per nucleon for each nucleus, you see a pattern. Plotting binding energy per nucleon on the y-axis, a nucleon number of protons plus the number of neutrons, on the x-axis you see a curve. At low nucleon level, hydrogen and helium and the isotopes all the way up to oxygen and iron, the binding energy per nucleon increases rapidly as nucleon number increases. The increase in binding energy per nucleon continues, but at a far slower rate as the nucleon number increases up to 56 or so, and that's the region that contains iron. After this point, the binding energy per nucleon starts to drop off. It starts to require less energy per nucleon to hold the nucleus together. Unlike the rise, the fall is much slower. It still requires a large amount of energy per nucleon to hold these larger nuclei together, but the amount per nucleon is decreasing. This means that if you split a very large nuclei apart into smaller nuclei, you have a release of binding energy. This peak in the binding energy per nucleon curve explains the energy changes driving the two nuclear energy production methods. If you combine very small nuclei together, you convert a large amount of the mass of these nuclei into binding energy. This energy production method is called nuclear fusion. If you split large nuclei apart, you are converting a smaller but still significant amount of the mass of these nuclei into binding energy. This energy production method is called fusion.